Hi everyone, welcome to my channel. In this video we're going to introduce binary addition. And falling under this topic we have the concept of a sign bit and the different forms that the magnitude of the binary number can take. We have a true magnitude form, a 1's complement form, and a 2's complement form. And with this foundation it's very easy to jump over to then binary subtraction, which is not much different than the ability to add two binary numbers together. So on a real basic level, let's compare decimal addition and binary addition. Now in decimal you have a lot more symbols representing numbers. So there are more cases that can occur with a carry over into the next position. With binary there are fewer cases because we only have two symbols that we use when counting, a 1 and a 0 in the binary system. So in this case we have an 8, and then when we add up the next position here we have a 12, which results in a carry of 1 into the next position. Now in binary we can only have two outcomes. We have a 0, which is no carry into the position, or we can have a 1 carried into the next position. So here we have a 1, and a 1 and a 1 results in a 0 with a carry of 1 into the next position. And a 1 plus 1 plus 1 in binary is equal to a 1 plus a carry of 1 into the next position. So we have a 1 and a 1, which is a 0, with a carry of 1 into the next position, which is now equal to 0 with a carry of 1 into the next position. So in fact, this here is equal to 15 in decimal. This is 22 in decimal. And this is equal to 37 in decimal. So if you work this out, we have a 1 in this position here, which is 2 to the 5th. So this is 2 to the 0, 1, 2, 3, 4, 5. This here is 32. This here is 4. And this position is 2 to the 0, which is a 1, which equals the 37. So that works out. So there are only 4 cases that can occur when adding two binary numbers at a time. Number 1, a 0 plus a 0 is equal to a 0. Number 2, a 1 plus a 0 equal to a 1. Number 3, a 1 plus a 1 will equal a 0 plus a carry of 1 into the next position. And 4, a 1 plus a 1 plus a 1 is equal to a 1 plus a carry of 1 into the next position. Now this last case, number 4, occurs when you have two 1's in a position and you have a carry from the previous position. You have a 1 carried from the previous position. That will result in adding 3 1's. So here we have two examples. We have a 0 and a 1, which is just a 1. A 1 and a 1 is a 0, plus we have a carry of 1 into the next position, and that gives us a 0 and a 1, and that's equal to 9 in decimal. And here we have 9. So we have a 1 and a 1, because 0, carry the 1. That's another 0, carry the 1, and another 0, carry the 1. And now we have a 1 and a carry of a 1. And that's equal to 24 in decimal. So you might be asking yourself, how do we add more than two numbers? Well, we don't need to. If we want to add another number, we add two numbers, get the result, and then add a third number to that. The power comes with the speed with which we're going to be able to do this in a microprocessor. So in this case here, we add the 9 and the 4, we end up with a result of 13, and then we can go and add 15 to that. We store this result, and then take the third number, and now we can add these two numbers together to get another result. In this case, this is 0, carry the 1, so 0, carry the 1, or the 1, carry the 1, and a 1 with a carry of a 1, which gives us 28. And then add another number to that result. And we're going to be able to do this very quickly. That's where the power comes from. And all other operations are going to derive from this ability to add two numbers at a time very quickly. From this basic operation of addition, we're going to be able to do subtraction, multiplication, division, and we're going to be able to do it very fast. In a previous video, we went over the topic of flip-flops, which give us the ability to store a binary number. So this could be 1, and the other Q0 is going to be 0, or this could be 0, and this could be 1. Now, if we can string these individual flip-flops together, we can then get a register, in this case, a 6-bit register, to store a 6-bit binary number. So in this register, we can count up to 1, 1, 1, 1, 1, 1. This allows us to count up to 2 to the n minus 1, which is 63 in decimal. So we've all heard whether a microprocessor is an 8-bit microprocessor, 16, 32, or 64-bit microprocessor. And that's telling us how large a binary number the microprocessor can manipulate at a time. And in this case, it's a 6-bit number that we're going to look at. So I could add two more positions here and make it an 8-bit register. And then that would give us the ability to work with numbers that were 2 to the 8 minus 1, which is 255. That would be the largest decimal number that we could manipulate with an 8-bit register. Now in the real world, we're going to be dealing with positive and negative numbers. So here we have the 6-bit storage register again, which allows us to store the largest magnitude number, or the binary number, is all ones, and that's equivalent to 2 to the 6 minus 1, which we determined was 63. So that's the magnitude, the highest magnitude number that we can store with a 6-bit register. So we need an agreed upon way of assigning a sign to this magnitude. So what we're going to do is we're going to add a sign bit to this magnitude. So we add another bit here, and we're going to have an agreement on what this bit can either be a 0 or a 1. So we're going to say that a 0 in this position will equal to a positive sign bit. So if there is a 0 here, this will indicate a plus 63. If there is a 1, that will designate that we have a negative sign. So if there is a 1 here, this will be indicating that it's a negative 63. So this is the sign bit. So to summarize, a 0 in the sign bit indicates a positive number, and a 1 in the sign bit indicates a negative number. So the sign bit indicates whether a stored binary number is positive or negative. For positive numbers, the rest of the bits, the magnitude portion, the rest of the bits always represent the true binary or true magnitude of the number. And the reason I'm saying this is because for negative numbers, the magnitude portion can have 3 different forms. For negative numbers, though, the magnitude can be represented in 3 different forms. We have a true magnitude form, a 1's complement form, and a 2's complement form. And we'll go over what these look like. In true magnitude form, the magnitude portion of a negative number is in true binary form. It hasn't changed. We still have the sign bit, which indicates that it's a negative number, but you can see that the magnitude portion between a positive 57 and a negative 57, the magnitude portion is the same. It's the sign bit that is telling us that this is a positive and this is minus 57. Now in the 1's complement form of a negative number, in this case say minus 57, we still have the minus 57 in decimal. What we do is we take the complement of each of the magnitude bits. So if it's a 1, we change it to a 0, and if it's a 0, we change it to a 1. So the complement of this number, this becomes a 0, this becomes a 1, 1, 0, 0, 0. And of course this is a 1, indicating that we have a negative number. So the 1, to get the 1's complement of minus 57, we take the complement of each individual magnitude bit. So you just take the opposite to get it into 1's complement form. So the 1's complement of any binary number is obtained by changing each 0 in the number to a 1 and each 1 in the number to a 0. Now we want to note that the sign bit is not complemented or changed, but remains a 1 to indicate a negative number. The 2's complement form of a negative number, here we have the magnitude and here we have the sign bit. We don't change the sign bit. To get the 2's complement of the magnitude of a negative number, we take its complement. So here we have 0, 1, 1, 0, 0, 0, which we now have the 1's complement. But to get to the 2's complement, we have an additional step. And the additional step is we add a 1 to that complement, that number that's been complemented. So here we have 1, 1, 1, 0, 0, 0, and we have the sign bit. So this is now minus 57 in 2's complement form. So in this case, here are the 3 different forms that the number minus 57 can take. Here we have minus 57 in true magnitude form, where we have the true magnitude or true binary form of the magnitude portion of the number and the 1 in the sign bit to indicate that it's a negative 57. And in this case, we've manipulated the magnitude portion and changed it into its 1's complement, which just consisted of taking the complement or the reverse or opposite of each bit in the magnitude. So we change the 1 to a 0, the 0 to a 1, 0 to a 1, 1 to a 0, and we still have the sign bit of 1. And last we have the 2's complement, where to get to the 2's complement, we have the 1's complement, and then we just add a 1 to the least significant bit position. And we still have the 1 in the sign bit indicating a negative number. So we have the true magnitude, the 1's complement, and the 2's complement form, in this particular case, minus 57, of the number minus 57. Now we're going to concentrate on using the 2's complement form of negative numbers because it has advantages over these other two forms of representing negative numbers that we'll show in a minute. The advantage of using the 2's complement system to represent negative numbers is that it gives us the ability to perform the operation of subtraction by only using the operation of addition. The benefit that we get from this is that we can use the same hardware or the same circuitry to perform the addition and subtraction operation. We don't need separate circuitry to subtract two binary numbers. So in the first case, we have two positive binary numbers that we're going to add. We can see here that each one has a 0 in the sign bit indicating a plus. So if we add these two together, we have a 1, 0, 1, 1, and the sign bit is 0. And in fact, here we have 13, and this is indicating it's a plus 13. So the sign bit remains a plus. In the second case, we're going to have a positive number and a smaller negative number added together. So here we have plus 9 and minus 4. So minus 4, we know, must be in 2's complement already. So minus 4 is 0, 1, 0, 0. And to get that into 2's complement form, we have to complement each of these bits and then also add a 1. So this becomes 0 carry the 1, 0 carry the 1, 1 with the sign bit. So you can see this is the 2's complement form of minus 4. So now let's add these two together. We have 1, 0, 1. Down to 0, carry the 1. 0, carry the 1. And also notice we have a carry here, which we just disregard. We just discard that carried bit position because this here is our sign bit. So this in fact is plus 5. And this is just discarded. And in the third case, we have a positive number and a larger negative number being added together. So here we have a negative 9, which is indicating that this binary number is in the 2's complement form of plus 9. So we know that plus 9 in its binary representation is 1, 0, 0, 1. And if we complement that, we have 0, 1, 1, 0. And to get to the 2's complement, we have to add a 1 to that. So we have 0, 1, 1, 1, which is in fact what we have here. So we still have the sign bit here is 1, indicating a negative number. And the magnitude portion here is the 2's complement representation. So now if we just add these two numbers together, we have 1, 1, 0, carry the 1, and a 1. So the sign bit is telling us that we have a negative number here, so the magnitude portion here must be in the 2's complement. So to see what the true magnitude form of this number is, we have to complement this again. So we have 0, 1, 0, 0, and then add a 1. That gets us back to the true binary form. So in fact, what we have here is 0, 1, 0, 1, which is 5, which in fact minus 4, which in fact minus 9 plus 4 is minus 5. So we have the 1 in the sign bit telling us that this is going to be in the 2's complement form. The magnitude portion will be in 2's complement form, and we verified that it's a 5 by just reversing the process. So we complemented again and then added a 1 to show that this in fact is a 5 in the true magnitude form. In the fourth case, we're going to add 2 negative numbers. So since these are 2 negative numbers, both of them are in 2's complement form. So all we have to do is add these together. We have 1 and a 1. This is a 0, carry the 1. This is a 0, carry the 1, and this is a 1. And then we have a 1 here that we're just going to discard. So just discard that. So this is telling us that we have the sign bit. We have a negative number. So this must be in 2's complement. So to check out the true magnitude form of this number, we're going to complement it and then add a 1, and we get 1, 1, 0, 1, which is 13 in decimal. So in fact, this is the 2's complement form of 13, minus 13. In the fifth case, we're going to add 2 equal and opposite numbers. So here we have minus 9, and this is the 2's complement binary representation. And here we have plus 9. So if we just go ahead and add these 2 numbers together, we have 0, carry the 1, 0, carry the 1, 0, carry the 1, 0, carry the 1, and a 0. And then we had a 1 that we just discard. 1 is carried. That's just discarded. And here we have 0. Now, subtraction in the 2's complement system, if you go look at some of the examples we've already done, we've already subtracted. It's just how you look at it. The subtraction operation in the 2's complement system involves the operation of addition. It only involves the operation of addition. That's one of the benefits of the 2's complement system. So the way we subtract a number is we take the 2's complement of the number you are subtracting, including the sign bit, and then just add it to the other number. So the number you're subtracting, if you take the 2's complement of it, if it's a positive number, that will change it into a negative number in 2's complement. If it's a negative number, it will then change it back into a positive number with a positive sign bit in true magnitude form. And we've already done that in some previous examples, except we were adding a negative number. Adding a negative number is the same as subtracting a positive number, and vice versa. So in this case, we have 2 positive numbers. We have a plus 9 and a plus 4, and they both have zeros in the sign bit. and these are in true magnitude form. So we can look at this in two different ways. We can have a plus 9, and we want to subtract a plus 4, or we have a plus 9 and we want to just add a minus 4. So to subtract 4 from 9, all we need to do is take the 2's complement of 4, including the sign bit. So this will change this to 1, 1, 0, 1, 1. We still have to add a 1, the final step, to get the 2's complement of the plus 4. And that will give us 0, carry the 1, 0, and 1, 1, 1. So that's the representation in 2's complement of minus 4. So now we can just have plus 9, which is 0, 1, 0, 0, 1. And we just need to add the minus 4, 1, 1, 1, 0, 0. We just add those together. We have 1, 0, 1, 0 carry the 1, 0 carry the 1. And here we have plus 5. So in order to subtract, we just need to add the 2's complement. And that's the benefit of using the 2's complement system to represent negative numbers. So in this video, we went over binary addition, and we're able to add binary numbers because we now have a way of storing the individual bits of a binary number in registers. But we needed to also represent the sign of the number, so we've added the sign bit. And then we have 3 different forms in which we can represent the negative number. We have a true magnitude form, a 1 complement form, and a 2's complement form. And we're using the 2's complement form because it has the benefits of allowing us to use the exact same circuitry to add and subtract 2 binary numbers. So we can either add a negative number or subtract a positive number. And when we use the 2's complement, it's very easy just to add the 2 numbers together to get the difference using the exact same circuitry that you would use to add the same 2 numbers. And we showed that how we go about using binary subtraction. So I hope you found this video helpful. Feel free to subscribe, like, and/or comment, and thanks for watching.